Uh, Hello, everyone. Am I audible? Hello, am I
Yes,
audible?
yes, you
Okay,
are.
thanks. Okay, so today's agenda for our session would focus on Gaussian mixture model and the estimation maximum likelihood of it. Estimation maximum algorithm. Okay, so in our last session, we have seen the estimation method. Okay, the general estimation technique that was for MLE, maximum likelihood estimator, and the Bayesian estimation. And that we see for our general distribution like Bernoulli, Gaussian, uniform, normal. So for that, we have seen our estimation method. We will do almost same thing today with the estimation, but now we will see a different type of distribution, that is the mixture model. Okay, so uh, how many of you have seen the lecture first? Did everybody here go through the lecture? Okay,
It's a three lectures.
okay, three lectures. Okay. Okay, so what we mean by the mixture model? Okay, so this means that our data set is or data points, our the sample data set is not coming from only one distribution. It is coming from many such distribution, and usually in many case, typically we will take the same family. Okay, so for here our GMM, this means our data set is coming from uh, normal distribution. Okay, and let's say if we have three normal distribution having all three of them having like different mean and variance. Okay, so our data set is generating from those three normal distribution. Okay, generally we take the same family class of distribution, but in general, as here we are taking the Gaussian, it is not necessary to be always to be Gaussian mixture model. We can have a distribution from other also like uniform, okay, exponential also. But for our course, we will only focus on the Gaussian mixture model. Okay, so let's start the session now. Hmm. So the key component about the Gaussian mixture model is, uh, yes, any doubt anyone? No. The key component about the Gaussian mixture model is, first of all, the Gaussian distribution, that we will have some k Gaussian distribution. Okay, we will refer them as the component. Okay, each Gaussian distribution in our mixture model will be referred as the word component. Okay, and each component, that means the each Gaussian distribution, okay, will have its own mean that we will refer as mu, and the variance sigma square. Okay, I hope the terminology is clear. The next thing is the mixture weight. Okay, which with what probability we will choose our component. Okay, and that probability is denoted by pi k. So if we have three component, that is three different normal distribution from which you are sampling your data set, then we will have pi 1, pi 2, and pi 3, each denoting the probability of selecting the distribution or the component from which you will sample the data set. Okay, and of course, as it is a probability, it will satisfy the condition that pi 1, pi 2 plus pi 3 till pi k for all the components, it will sum up to 1. The next main thing is the PDF for the GMM. Okay, maybe we will come to this part a little later. Okay, what this PDF actually means. Okay, but for that, if you want to understand this, it is basically the probability by which you select your component multiplied with uh, the PDF of the normal distribution from which you are sampling. Okay, and we will sum this up for all components. Okay, as with the PDF of the GMM, this N here, the stylish N here will denote the PDF of the Gaussian distribution. with mean mu k and sigma square k, because each component will have its own mean and variance. So that's why we are denoting it by mu subscript k, sigma square subscript k. And pi k, okay, is the prior contribution of the kth component. Okay, this prior term, how we are select or saying this as the prior probability type. Okay, just wait for a few minutes. These things will be clear as we will go next. Okay. So we will discuss this PDF thing, okay, in detail in few minutes. Okay, just bear with me for a few more minutes. So the story how you will sample from your GMM. Okay, it's a two-step process for sampling the data points from your Gaussian mixture model. Okay, that is, first you have to select or choose the component. Okay, and as I said, this selecting the component, okay, choosing from which component you will sample, okay, choosing from which Gaussian distribution you will be sampling your data point is called a prior probability, which is denoted by pi k. So that is our first step, that you will choose from which component you have to sample. Then you will sample your point from that Gaussian distribution, and that is basically the conditional density. Okay, conditional, because what you are doing, it is given like, first you choose the component, then given that you have chosen this component, okay, you will sample your data point from that normal distribution. Okay, so that's why it is a conditional density, that given you have chosen this component, you are sampling from your data point from that component, and that is the density function of your the normal distribution. Okay, uh, till now that the story clear to all of you how you sample from the GMM. Okay, if this part is not clear till now, we will look at few examples and maybe after that it will be clear, but I hope the sampling from GMM is clear to everyone. First you choose the component, and then you will sample your data point from the choosed component. Is it clear to all of you?
Yes.
Thank you. Now, the part that we will now focus on our terms and look at few examples of to understand better. Okay. So example one, we have taken the pi 1 and pi 2. Okay, pi 1 and pi 2 is the probability for choosing the component, and here both are 0.5, 0.5. That means there are equal chances for choosing any component. Okay, mu 1 and sigma square 1 denotes the normal uh, parameter for the component 1, and mu 2 and sigma square 2 are the parameter for our Gaussian distribution of the second component. Okay, now if you look at this graph, let's focus on this. Okay, this dotted region that you are able to see, okay, these are basically the graph or the density function graph of your normal distribution only. Okay, so this dotted region is your component 1. Okay, if you just focus on this region here. Okay, and this is your component 2, while this green curve here, that is uh this curve. Okay, this is the GMM. Now can anybody tell me why it is shrink like this? Can anybody guess the reason behind this? What's the reason behind for this scaling? Because our first component look like this, second component look like this, while if you take the GMM graph or GMM density, okay, it would be shrink like this. Can anybody try to guess what's the reason behind this? It is
Whether it
green.
is always below the original class.
Uh, Not always, but yeah, see, it would be in some case, yeah, it would be like you can say, but what's the reason behind it? Okay, the reason is hidden in how you sample from your what we say GMM. Okay, the density function of GMM. Okay, that's okay. So the reason is, if we go back a little on this density function. Okay, how this density function of GMM is defined? Okay, it is some scaled. Okay, it's not like we are just adding the PDF of the normal distribution. We are weighting them up with the probability of selecting that component, right? That is the pi k. Okay, it's not the simple addition of your normal distribution. We are weighting them up with some probability, that is the probability for choosing that component, and then we are adding those up. Okay, so this shrinking of the GMM is coming from there because we are adding them here with 0.5 probability. Okay, so 0.5 times the n1, that is the normal distribution first, plus 0.5 times n2. Okay, so now if we will try to write the density function for this GMM that we have plotted here. Okay, how it will look? It will be pi1 into your xi data point from mu1 comma sigma 1 square plus pi2 times mu2 comma sigma 2 square. Okay, is this density part clear? How the density for the normal distribution will look like here? So try finishing by 8. We by 8 it would, yeah, this slide we can end by 8, but the programming assignment I guess it will be a little bit more. Okay, slides we will try to finish before it. Now if we just put the value here, okay, the values that were given to us in this density function, so maybe the equation look terrible, but just understand pi1 is given to us as 0.5. Now what is the density function for normal distribution? What is the density function for normal distribution?
1 by root 2 sigma pi root 2 pi sigma
Mhm.
xi minus mu 1 minus xi minus u1 the whole square upon 2 root sigma square.
And this will go in exponential power. Okay. Yeah.
Yeah.
So it is 1 by root 2 pi sigma square. Okay. Exp means it is e power. Okay. Minus xi. Okay. So let's just keep it as x minus mu square. So mu1 is what? Mu1 is -1. So it will just become +1. Okay. And divided by 2 sigma square. Okay, square root of 2 sigma square. So here it is 1 by 20. So it would become here 1 by 10. Okay, this squaring here. Now same thing will come for 1 by, okay, sigma square. So let's replace the sigma here with the actual value that we have given. 1 by 20. Okay, so it will become 5 by 10. Here also it will become, okay, 5 by 2. So mu2 is 1. So x minus 1 square divided by, okay, so 1 by 2. Okay, so this is how the density function will look like. Okay, what I did, I just put the density function of the normal distribution. Okay, and nothing else. It's the same expression with values of whatever we have given to above. Okay. Hmm. Okay. Let's move toward and understand each term that involves in the GMM. Okay. Whether it is in the prior probability, conditional probability, marginal probability. Okay. So
Sir,
first of all,
can you
yeah.
summarize once why did the JMM shrink?
Okay. So see, in GMM, this is the density function of GMM. Okay. We will look how this density function we arrived. Okay. A little later. But how it's not like we are just adding all the normal distribution directly. Okay. This function is not like just we are adding n1 plus n2. Okay. Till whatever n come if let's say you have k components, so nk. Okay. We are scaling them by the prior probability. Okay. That is the probability of choosing the component. Okay. We are multiplying each with that. Okay. And then we are adding them now. So this is actually like pi1 n1 plus pi2 n2. Okay, times pi k n k. Okay, that's what it basically means by this function. Okay, so as we are multiplying them with the probability of choosing that component and then adding them up. Okay, so that's why it got shrink. Okay, we are not just directly adding those two normal distribution. Okay, we are scaling them by some number and then we are. Okay,
Okay, sir, got it. Thank you.
now let's understand each term involved in GMM in a little more detail. So first of all, we will consider that we have k components. Okay, that is from 1, 2 till k. We have k components. Now the PMF of Z, that is the prior probability. Okay, the prior probability means the choosing component. Okay, probability of choosing any component. Okay, Z here will denotes the component indicator. So just like in K means algorithm in the last week we have seen, we are also describing the cluster indicator through ZI, right? So here also we are describing the component indicator through Z only. Okay. And later in the end of the session, we will see how similar the EM and K means works. Okay. We will see that at the end of the session also. Now Z here denotes the component indicator. So that prior probability of selecting the uh, component is given by pi k. What does this mean? There is pi k chance that a data point is going to picked up from the kth component. So that means here if we see for any component there, if we are choosing it pi1 denotes the probability of choosing your data point from the first component, pi2 denotes the choosing probability of choosing your data point from the second component. Okay, just like pi k, it denotes the chance that a data point is going to picked up from the kth component. Now the conditional density part. Okay, given that you have chosen your component, now what is the next step? You will sample your data point from that component, and because we are what we have Gaussian distribution for each component. Okay, so the conditional probability that given that you have picked the component, now you have to sample your data set. So the conditional density is the probability of observing the data point X. Okay, that is how likely is it for X to come from the component K. Okay, is the conditional density part clear? Given that we have chosen the component K, what is the probability of or density for point Xi? Okay, and that follows the normal distribution. Now the joint density. Okay, so before the joint density, uh, tell me how you can write the joint density function in terms of conditional and marginal. Okay, if x and z are some random variable, then if you want to find the joint density between x and z, okay, how you can write that joint density in terms of the conditional and marginal density? Is it conditional by marginal, conditional into marginal? How you write? Okay. So the joint density is equal to conditional into marginal, because see, uh, let's say if you're given the conditional density, okay, that probability of A given B, how you write that? Probability of A and B divided by probability of B. Okay. Now what you want? You want the joint. Okay. So the joint would be conditional. Okay. Times marginal. Okay. So if you want to find the joint density, that would be same as conditional density into marginal. This we have seen in stats 1 and stats 2. I hope you guys remember. Okay. So we will be finding the joint density of X and Z. X here denotes the PDF. Oh, yeah, PDF of GMM, and Z is the prior probability of choosing the component. If you want to see the joint density, that would be same as marginal times the conditional. Okay, we have seen the conditional here, so this conditional comes from here. We have seen this marginal here, that is pi k. Okay, so is the joint density part clear to everyone? I hope.
Yes.
Yeah. Now, what the mean we differ from it is pick a component k and sample a point x from it. Okay, that's what the joint. Now comes to the marginal density or the density of GMM. Okay, so this we have seen before. Now we will talk about it. This is the density for one component. Oh, sorry, one data point. Okay, that you just pick a component k and sample a point from x from it. But the x point that you are sampling can may have come from any of the component. Okay, so what you will do, you will sum this up across all the components that you have. Okay, and that's how you will basically get your density function of GMM. Okay, we just sum up the joint density between x and z across all the components. Okay, and that's how you will get the density of the GMM. Okay, because the point xi could have come from any of the components, so we will just sum our joint density function across all the components. Okay, and that's what I have written here. Okay, this was basically the form that we have seen here. Okay, conditional into marginal, and it was in the joint form. Okay, only the notations are different, and this was the form that I wrote before here. Okay. This is the density function for the GMM, that as the point xi could have come from any of the component, so we will sum across the joint density function across all components. Okay, so that would be pi 1 n1 plus pi 2 n2 till the pi k nk. Okay, n1 n2 means the normal distribution. Is the marginal density clear? Okay, good. Now the final thing, that is again the conditional density, but this time it is a different conditional density. Okay, before our conditional density was that you are choosing one component, and then what is the probability of x belonging to that. Now this conditional density is what, given you have point xi. Okay, given you have the point data point, what is the probability that it has come from the cluster k? given the data point x, what is the probability that it has come from component K? And that is given by this. Now, this might look terrible to understand. So let's break down this equation into some pieces. Okay. So you have this function here. That is, this is the density that you want to find as z given x. Okay. So conditional is joint and divided by marginal. Okay. Or using the Bayes theorem, how you can write this as? You can write this as fzk times x given z divided by fx. Okay. What we did here was the Bayes theorem. Okay. So Bayes theorem, we remind probability of A given B is uh, probability of A times probability of B given A divided by probability of B. Okay. This was the Bayes theorem. So if you see this term, fzk is the prior probability, that is the probability of choosing the component. Okay. So this term is nothing here but the pi k. Okay. This here fx given z, that is given that you have chosen the component, the probability of data point coming from that. And what is this? What would be this probability?
Likelihood.
Given yes, what is uh,
Likelihood.
yeah, this would be kind of likelihood, but it would be the normal here. Okay, this is denotes the normal distribution. Okay, this can also be seen as likelihood also. Okay, because it is like prior probability times the likelihood divided by the evidence. Okay, we will get into that part also later, but we have seen this probability here. Okay, this is the conditional density, that given that you have chosen the component k, the probability of your data point. Okay, that is the normal. Okay, so this was the pi k. This was you are sampling your data point from that normal distribution, so it is nk. Okay, from the kth component you are sampling, and it is the fx, so that is the density of GMM. Okay, so sum across all the components. So maybe in more good terms, you can write this probability as, let's say, pi k nk divided by sum of sum I equal to 1 till k. Okay, pi k, equal pi k nk. Okay, so this comes from the Bayes theorem. Till this now, is it clear to everyone? Any doubt, anyone, about the terminologies? Okay, the conditional, joint, marginal. Okay, so the parameters of the GMM, even though we have seen this already, that as you have k component, so for each component you will have these three. You will have the probability of selecting the component, okay, and the mean and the variance of that component. Okay, so as you will have k component and each component will have three parameter associated with it, So there would be 3k parameters. But why did I add -1 here? What is the reason for adding the -1? I will rephrase my question again. What we are doing here is counting the total number of parameters that we have to estimate for the GMM. Okay. So as for each component k, there would be the probability of choosing the component. Okay. And the mean and the variance of that component. Okay. So as we will have k component, so the total parameter would be 3 times k. Okay. But why I have written here 3k minus 1?
So because the summation of pi's is equal to 1, so last
Yeah.
we could get if you know n minus 1 pi's.
Yeah. Good. Okay. Because these pi k's are the probability of choosing the component and we have written in this above. There's these will sum up to 1. Okay. So that's why one parameter is uh, we can find. If you have like till pi k minus 1, then the last probability we can find using 1 minus that. So that's why there's only 3k minus 1 free parameters that we have to estimate. Okay. Just focus on this part here, that here in the GMM, our parameters do not increase with respect to the number of data points. Okay. They are increasing with respect to the number of components that you will have. Okay. The number of parameters to increase here are dependent upon the k. K denotes the number of components. Okay. So 3k minus 1. And we will denote these parameter using theta. Okay. When we will go for the EM part. Okay. We will use the notation theta to, to bundle all the parameters in one notation. Okay. This we will use later. Now let's look at few more examples to understand it more, especially the part of the why we call the prior probability. Okay, choosing the component, why it is called as the prior probability. And we'll look at few more points about the GMM structure. So let's look at first this GMM1, this graph that is given to you. Okay, so what can you say about the probabilities of selecting the component just by looking at the graph? What is your belief about that? Yes, Emma?
Both are the same probability, sir.
Yeah, correct. Okay. So the belief that you can make by looking at the structure of the GMM from this is that that we have the same probability of choosing the component here. Okay. So why? But that means that pi1 equal to pi2 equal to 0.5. Okay. What about mean of, okay, what about mu1? What would it be mu1 here? Mu1 is the mean of the first component. Okay. So what would be the mu1? Just look at the graph and try to identify. By first component means this side. Okay, left hand side is the first most. Just think how you will just treat this like a some normal bell curve. Okay, how will you find the mean from that?
Minus 1 and 1, sir.
Yeah, correct. Okay, because if you see uh, the structure, okay, -1 is here. That is kind of the mean of that, and 1 for the second. Okay, so mu1 is -1, mu2 is 1. What about sigma 1 square? Okay, so that is something we cannot tell. Okay, so I will just write that. So they were also the same for there. Okay, we cannot exactly tell what is the variance here would be. Okay, but as I generated this graph, so I know. Okay. Now let's look at the second one. This GMM2. What can you tell about again? First, what can you tell about the probability distribution for about choosing the component? Okay, from left and right. I don't want the exact answer. Of course, you cannot guess the exact, but around something. What do you think? Around what should be the probability of choosing the component 1, and what can be the probability of choosing the component 2?
The probability of choosing one is higher than the probability of choosing
Yeah,
two.
that is higher. But can you guess any number around which it should be? Oh, 0.7, 0.3. Okay. Good. The real that from with probability I draw this graph was 0.8 and 0.2. Okay. So of course you cannot guess the exact one. I just wanted you to estimate. Okay. So are you all able to see how there the how this choosing the component is some sense of prior probability here? Okay. You can get the info like how many if you have some data points that are coming from the GMM, then with the probability of choosing the component, you can get, yeah, almost if you have 100 data points, 80 data points are likely to come from the first component and 20 data points are likely to come from the second component. Okay. So that's why the choosing component, okay, just choosing a component is called the prior probability. Okay. So from Bayesian estimation, if you remember the prior probability, that is the belief that we have before. Now, what would be the mean and what would be the mean of mu1 and mu2? Component 1 and component 2?
Is it the same? Minus one
Yeah,
and
it's the same. Both are same actually. The I just only changed the both are same.
Sir, how we are determining pi, sir?
Pi. Okay, so see, you cannot tell directly from the graph what exactly value is, but yeah, you just know that the pi one, that is choosing the data point from the first component, would be higher than the choosing the data point from the second component.
Are
So
we
you
comparing
can
the areas under curve or what, sir?
you are, yeah, kind of like that you can understand. Okay, the higher the peak that it will having. Okay, there are chances that the data points are coming from that. Okay, of course that's
But
not the only. Yeah,
if the height is less and if it is more broader, so should we consider area under curve or what?
yeah, that's what we are coming into that. Of course, not only the what we say, the height can consider as a scenario because variance is also one matter that affects. Okay, so but these are just the toy data set. Okay, so that I generated and the variance are same for all of them. Okay, so only the height that will matter here. Okay, but in general, of course, variance will also affect the height because if variance is more than the data set are more spread or something. Okay, but as here the variance of the data set are same, so the height will get more weightage. Okay, and based on that you will guess that what is the which component has the more dominance here.
Okay, sir. Thank you.
Okay, but of course the variance part will also matter here. Okay, that's what I was coming. Now again, okay, this was the same. I just kept it up here. This left hand side is the same as what we see. Now what about this one? What can you guess from here? What is the probability of choosing first component, the probability of choosing the second component?
9.8 or 9.9, and second one 0.1, 0.1.
Not 9.8, you mean zero point 0.9, right?
Yeah, yeah,
Not,
sorry, sorry. 0.9. Yeah, sorry.
yeah. And it is exactly what it is. The probability of choosing the first component is 0.99, and from 2 it was like 0.01. Okay. So the mean and the variance are again the same. Okay. Now, if you just see what is happening here is, as there's very less data point that is coming from the second component, but only there's just one bulk is there. Okay, and it almost like there's only one component. Okay, it almost feel like there's only one component, and it's like just your normal distribution instead of the GMM, that is mixture model. Okay. Again, one more example, final example. Now, what about this? What do you think about the probability of selecting the component here?
Two components are merged, is it?
Yes, that's what GMM do. Okay, it's just that yeah. In before it was quite easy to distinguish between two. Now, as the Lakshya said, it is 0.5 for both. Okay, both the pi1 and pi2 are 0.5 here. Okay, now it's just that here they will have something different, that is the mean. Okay, what can you guess for the mu1? Okay, what is mu1?
0, sir.
0, correct. Okay, what about mu2?
0.5.
0.5.
Yeah, it is close to 0.5, 0.7. Okay, variance I will just type. In all the graph we have taken the variance, and that's why we can easily compare these two. Okay? Now the last example. Okay, what is the probability of selecting the first component and what is the probability of selecting the second component? I just need a guess, not the exact value.
0.3, 0.7.
Yeah, correct. Okay, this time it is exactly what it is, 0.3 and 0.7. Okay, what about mean?
Same as earlier.
0.
0 and 0.7.
It is the same. Okay, now one thing that if you check from here, okay, these two graphs, while the one that we discuss here, okay, not this one, okay. Here also, if you see the probability of selecting the first and second component are same. And here also the probability of selecting the first and second component are same. The reason, but if you see, in this graph, it's not easy to distinguish between the two components. While in the first graph that we saw, it is very easy to distinguish between two components, right? They were clearly distinguishable. Okay, so it's almost like you can say that you can draw one line at the 0 and all the data points that are negative will come from the component 1 and all the data points that are positive will come from component 2, right? From this graph you can tell, right? While in this it is not that distinguishable, just like how it was in the first case. Okay, and here also it is not that much distinguishable. Okay, the info that you should refer from this is the farther the mean are, okay, here the mean are very close, while in the first graph the mean were far away from each other. The farther the mean are, it is easy to distinguishable between two components, while the closer they are, it is not easy. Okay, of course there are other parameters also that will affect. Okay, so just like for the probability, as the variance will also affect the probability of choosing the component, but just for the two example data set, if you understand, okay, the farther the meaner, the easy it would get you to distinguish between two components, while the closer they are, it would be not that easy. Did everybody get this point? Okay, now one question, did we talk about this before in any week? In any week, did we talk about this before? the farther the meaner, the better it is to distinguish between something.
So k-means.
Yeah, correct. Okay. In k-means also, if you remember the initialization part, what especially in k-means plus plus, we go with the probability way, and the probability was to choose the second cluster centroid to be as far as from the first cluster centroid. Okay. So in the end also, we will just compare both the EM algorithm and k-means, how they similar. Okay, how they are similar also. Okay. So just to remember this point. Okay. So this is just to you guys to relate between EM and k-means. Okay. Now the prior and the posterior part. Okay. So from the Bayesian estimation, okay, the posterior probability is that given you have data point, okay, what is the probability that it is coming from the component K? Okay, that we have seen before. Okay, when we discuss the terminologies, that it is the joint. Okay, conditional is what? Joint divided by marginal, and you can write this joint also as conditional into marginal. Okay, or maybe directly you can go from here to here by using Bayes theorem. Okay, using Bayes theorem also you can directly go from here. Okay, what this means, it is a prior probability of choosing the component multiplied with the conditional here, or what we will say here, likelihood term, that is given you have chosen the component K, the probability of selecting your data point from that component. Okay, that is follows the normal, and denotes in the denominator we will sum across all the probabilities that just data point could have from component 1, 2, 3. Okay, so we'll sum over those, and that would be our denominator. I hope this part is clear. Okay, or if you want we can write one sample, like uh, for pi1 it would be like pi1 and xi mu1 sigma 1 square divided by pi1 and xi mu1 sigma 1 square plus pi2 xi mu2 sigma 2 square. Okay, so I have written this one case for the, if you just want to find that what is the probability that given one data points is coming from the first cluster. Okay, this is the probability of that your point xi is coming from the first cluster. So probability of choosing the first cluster multiplied with the normal density function. Okay, and in the denominator we will divide by both. Okay, given that initially we have only two clusters. Okay, so I hope this conditional density part is clear, and the prior and the posterior also to everyone. Okay. So let's look at few examples again. So this is the density function of the GMM that is given to us with these parameters 0.8, 0.2, mu is 1 minus 1, and sigma 1, sigma 2 are 1 by 20, 1 by 20. Okay. Now, if you want to check whether the negative 0.1 has come from the first cluster, how will you check? You will put pi1 value. Okay, pi1 value is 0.8. Oh, okay, I guess it is wrong here. It should be 0.5. 0.5 for both. Okay, so if you want to check whether the negative 0.1 has come from the first cluster, okay, that's what it is asking here. So you will put 0.5 multiplied with your, what are the parameters, 1 and 1 by 20. So 1 and 1 by 20 divided by 0.5 into normal 1 comma 1 by 20 plus 0.5 into minus 1 comma n of minus 1 1 by 20. Okay, you will solve this equation. That is, first calculate the normal density function value at mu1 and sigma 1 by 20. Okay, and same for denominator. Okay, and just expand this equation, and that would give you the probability that the point negative 0.1 is coming from the cluster 1. Okay, is the part clear to you how you calculate the probability? That is this conditional probability. Okay, you will find this question more in your quizzes also and in assignment also. Okay, this type of question is frequently asked. Okay, you will be given the point and you will be asked to calculate the probability that this data point could have come from the cluster 1, 2 or something like that. Okay, so I hope this is clear to everyone.
How you wrote the normal?
You will have to calculate the normal distribution value, like, okay, given the density function. Okay, given the density function of normal distribution, 1 by square root 2 pi sigma, okay, multiplied with exponential power minus x minus mu by whole square divided by 2 sigma square. Okay, so with that you have to calculate. And sometimes in the exam also we might give you the normal function value. Okay, what would be the Gaussian distribution value on these points? Okay, sometimes you might give you, but sometimes you might have to calculate by yourself. Okay, because you have the calculator there. Okay, I'm not going to calculate here because it will take too much time. Maybe you try calculating this value and fill up this table. Okay, when I will upload this document, okay, this document will have the answer for this. Okay, but I will appreciate you guys if you try them by yourself. Okay, but maybe we can discuss this part. What would be the probability that the 0 is coming from the first cluster? Given that here the data point 0, what is the probability that it would come from the first cluster? Sorry, first component. Any guess that you can make?
0.5.
Yeah, correct. Okay, 0.5. It would be just 0.5. Okay. Now, what about, okay, what can you tell any relation about these two? Okay, that is the negative 0.1 coming from the first cluster and 0.1 coming from the first cluster. Can you discuss any
They,
probability relation?
they both are the same. I guess 0.25.
Sir,
Yeah,
coming from the second or first?
first, both.
Let's
Okay, for
check.
both. Yes.
Probably for
Symmetric.
minus 0.1 will be more, and for 0.1 it will be less.
Yeah, that's the correct relation. Okay, and that's what we talked about before, that when you have separate, okay, because here see,
Said how,
you can clearly, yes, yeah, yes,
said
Ravi.
how we got, he said how we got 0.5 for 0.
0 is because kind of like middle, okay, in the middle of that. Or if you are unsure about, if you just put it this here, okay, what it would be, uh, if you go back to the normal, okay, the normal distribution for mu and sigma square, okay, it is like uh, sigma root 2 pi, okay, exp minus x minus mu all square by 2 sigma square. Okay, this is the normal density function. Okay, now if you see, the sigma is same for both. Okay, what you have here is just the mu. Okay, pi k is also same for both. Okay, so when you try to find for the 0 and put this here, okay, in this equation, the pi 1 are same. Okay, the sigma square are same, only the mu is different. But if you go back to this normal density function, what you will get here, 0 minus 1 or 0 minus minus 1. Okay, and both case you will get the same result, right?
Yes, sir. Yeah.
Okay, so it would be half. Okay, because they both here would be same, so it would be just half. Got it? Or maybe if you are still unsure, just try calculating once is by yourself. Okay, okay. Now the reason why the negative will have the high probability for coming from cluster 1 while the positive will have low. because here, if you see, you can clearly separate your components, okay? As you can discuss before that, it's more likely that the negative data points are coming from the cluster 1 and the positive data points are coming from the cluster 2, okay? So that's why the probability that this negative 0.1 would come from the cluster 1 would be high than about the positive, okay? And once you try calculating this value, you will get that this is approximately like around 0.9 or something, and it is very less, okay?
Sir, can we think that if we plot the area, it goes on decreasing as we move
If
from
you
left to right?
okay, as you move from left to right,
The
I
area
will
under
not.
curve for the left one, when we point to minus 0.1 and move towards 0.1,
Hmm.
that
Yeah.
curve goes on descending and that
Mhm.
area goes decreasing. So that's why it could be said that probability.
And now see here, because the two components are clearly separable, so maybe you can say that, but it's not necessary to be in general, okay? Yeah, the two components are separated because one is cover the negative part, one is cover the positive part. So maybe here you can say that kind of, okay?
Okay, sir.
Okay, we have one more example. Okay, so what about this one? Can you say anything here? Okay. We cannot say anything here about like what is the chances or might the relation between these points. Okay, so I will give this as an homework. Try calculating these value by yourselves. Okay, yeah, but okay, so maybe we will just okay, this is not up to scale. So okay, so these two are homework for you. Okay, when I will upload this PDF, uh, in that uploaded PDF, it will have the value. Okay, but try calculating these by yourself first. Okay, these probabilities. Okay, I've given you the idea how you will calculate it. Okay, maybe you can use Colab if you want. Okay, you can write the function for normal distribution and to calculate the normal density function value. Okay, if you feel uncomfortable with that. The reason of confusion that we talked about, the farther the mean are, okay, the better it is to make distinguish between two components. Okay, and the closer the mean are, the greater potential for confusion. Okay. Okay. So, but of course, it will not just directly depend upon the mean. Okay, mixture probability also takes some part. Okay, how the which component has more dominance probability. Okay, but in general, if you just have two components and with the same probability of choosing the component, okay, then if the means are closer, it would be create a confusion to distinguish between them. But if they are farther apart, you can easily distinguish between that you have two components. Okay, till now, does anybody has any doubt whatever we discussed till now? Okay, no, good. Now we will move on to the part. Till now, what we did was to understand the distribution of the Gaussian mixture model. Just like we have Bernoulli normal exponential distribution. Now, what we will move on to the estimating the parameters. Okay. So in our last session, we estimated the parameter for Bernoulli normal uniform. Okay. Using the MLE and the Bayesian method. Okay. Here also we will go towards estimating the parameters of the GMM. Okay. So given that you have data set x1 till xn, which is sampled from the GMM Gaussian mixture model. Again, our IID assumption independent and identically distributed. I hope you remember what independence and identically distributed means. Okay, with k components. Okay, so this we have already discussed that we will denote our parameter with just theta Okay, and there are 3k minus 1 free parameters that we have to estimate. Okay. Prior probability times the probability of norm component. Okay, that is the density function. Now if we are going with the MLE way. Okay, so for MLE we have to calculate the likelihood function. Okay, so the likelihood function, likelihood is a function of parameters. Again, I will remind you. Okay, it is a function of parameter given the theta. So it would be the product of all density functions. Okay, given your parameter theta. Okay. Okay, I hope this part is clear how you calculate the likelihood function. Now, if we want to expand this, so this equation would become very ugly. Summation from I equal to, okay, let's use k. Pi k times psi mu k sigma squared k. Okay, I just did nothing. Just put this PDF of the density function here. Okay. Now, what's the next step that you will do in MLE?
Take log, sir, both.
Okay. So we will be taking log both side here also. Now we will denote the log likelihood function with small l. Okay. And we will take the log on this term. Okay. Fx theta. Okay. And if you expand this, now due to this log, this multiplication would become what?
Summation.
It would summation. Correct. Okay. So this will turn into the summation. From I equal to 1 to n. Okay. And the log will go here on fx theta. Okay. Now if we just copy paste our density function, log of, okay, not I, k equal to 1, k pi k xi mu k sigma square k. This is our log likelihood function for GMM. Okay. Now what's the problem here?
Inside log functions.
Yeah. Okay. We have this summation inside the log. If this summation would not be in here, we can just simply it would be like simply estimating our normal distribution. But because of this summation, we are stuck here. Okay. So we have to find some another way to get over this summation. And those who have watched the lecture, can anybody of them tell me what's the way the prof did? What's the process?
Jensen is the solution, sir.
Yeah. So Jensen's inequality comes into the picture here. Okay. Now what it means by Jensen's inequality, if we look at from the logarithm function point of view, what I have here is on the screen is we have drawn the graph for the logarithm function. Okay. So log of this. Okay. This this blue curve here represents the logarithm function. Okay. This is the graph for logarithm. It's base 10. Okay. Now this straight line is the line joining the point log 2 and log 5. Okay. So they will intersect them here. Now the Jensen inequality say that if you have any function that is basically the concave function. Concave function means the maximum occur in that function. Okay. So here we have the example for the logarithm function as they are increasing function. Okay. So if you take any 2 point on this logarithm curve, as here we have taken these 2 points, log 2 and log 5, and you draw the line joining these 2 points, okay, that line will always stay under the curve of the function. Okay, if you have any concave function, and if you pick any 2 function on any 2 point on that function curve and join those points using a straight line, that straight line will always lie below the curve. Okay, and if this happens, this also implies that it is a concave function. If the straight line always lie above the curve, what that function would be? What type of function? If the straight line would lie above the curve.
Sir, it will be concave function.
No,
What is
the
the
above.
question, sir?
So convex,
If,
sir.
yeah,
Above
convex it
the
is. Yeah. Okay, if the straight line lie below the curve, then it is a concave function. If
this
the
is
straight line
concave
lie
function.
above the curve, then it is a
Yes,
convex
that is
function.
convex function.
Yeah. Like for example, if you just take the parabola, okay, and if you draw any straight line, okay, on any 2 point on the curve, it is not necessary that it should satisfy only 1 or 2 points. Okay, it should satisfy for any point on the 2 curve. Okay, any 2 point on the curve, if you join them and draw the straight line, okay, it will always lie below, oh sorry, it will always lie above the curve. Okay, only between the region of those points. Okay, so if you see, I've chosen this point, and only below this region, this straight line will always lie above the curve. This is, if this happens, it is a convex function. But if this happens, that is, the straight line joining those points lie below the curve, it is a concave function. Okay, and we will be using the concave function scenario here. Okay, as you can see, logarithm is a concave function. Okay, that is, if you pick any 2 point on the curve, on the logarithm curve, okay, and draw a straight line joining that point, that straight line will always lie below the curve between the region of those 2 points. Okay, one more condition that it should satisfy that uh, you will be doing like so the actual then what I say inequality is like this: log of lambda, okay, so log of lambda times x1 plus lambda 2 x2 would be greater than equal to lambda 1 log of x1 plus lambda 2 log of x2. Okay, so this is the inequality form. Okay,
Sir, please explain this, how we have written this below this
okay, this is
Jensen's
basically
inequality.
the Jensen inequality form. Okay,
Above, sir,
and it's
the
above
line one above that.
this, you mean?
Yes, yes.
Okay, do you understand this form? Okay, this is the form of Jensen inequality. It's
Yes,
just that
yes.
here I have taken the some point. Okay, that is for lambda 1 and lambda 2, I have chosen them 1 by 2, 1 by 2, and this x1 and x2, I have chosen them 2 and 5.
Okay,
Okay,
now got
so
it, sir.
lambda,
Those are
okay,
lambdas.
okay.
Okay, sir.
There's one more condition that this lambda 1 plus lambda 2 should also sum equal to,
One.
yeah, okay. Only under this scenario, okay, this will happen, that if you choose any 2 points and scale them by from lambdas such that the lambda values sum up to 1, okay, then the straight line joining them will always lie below the curve, okay, in the case of concave, and in the case of convex, it will lie above the curve. We don't care about the convex part here, okay, that part those who have done MLF must have studied in MLF. If you have not done MLF, you will study that in week 9 of MLF, okay. But this is the Jensen inequality part that we will be using, okay, to get rid of the summation inside the log. Okay, so just keep looking this slide. Okay, now it's some the is kind of like a heavy point here. Okay, if you understand till here, maybe you will understand the EM part also. So this was our logarithm, oh sorry, log likelihood function. Okay, that is summation from I equal to 1 to n, log of summation from I equal to 1 to k, pi k times normal. Okay, problem was there's summation inside the log. Okay, to get rid of that, we are going to the Jensen inequality form. So what we will be doing here, those who have watched the lecture, what trick does professor did here to first compare it with the Jensen inequality form. He introduced one more variable, okay, that is lambda ik. Okay, we will introduce this new variable, okay, and just look at this form. Okay, just compare what we are doing here. We are multiplying and dividing by lambda ik. Is this going to affect anything here? No, right? If you multiply and divide by the thing, it will not affect. Okay, now we will compare this with the Jensen inequality form. That is, we have log of lambda i's plus this, okay, and using the Jensen inequality, this would be greater than equal to this. Okay, so here we have taken the two lambdas. Okay, it can go till n number of times. So that's what we did here. This quantity would be greater than equal to, now this lambda ik will come out and it will be just log of this inner part. Till from here to here, clear to all of you? How did we go from here to here? We use Jensen inequality and the log of lambda I xi, okay, treat this whole thing, let's say some variable, okay, y. So using Jensen inequality, this would be greater than equal to, this lambda will comes out and the inner part, this was here, will remain here as it is. Okay, using Jensen's inequality. Is this part clear to everyone till now? Okay, now, okay. So just look at this part here. What is happening that we have some lambda ik, okay, and if you remember, it is denotes also the probability. Okay, it's not like we are randomly introducing anything. This we will later see that it also denotes the conditional probability. Okay, those who have watched the lecture might have understood. Okay, so this lambda ik we are multiplying with this, okay, and we are summing that up for all I equal to 1 to n. Okay, does this form looks familiar? We are multiplying the probability, okay, some probability with the random variable value, and we are summing them up for all data points. Is this form look similar? Just give me 1 minute, okay. Yeah, okay. Sorry for the disturbance. So I was asking the question, does this form look similar to anyone? That we have this lambda ik, which is kind of like probability, okay? And this value, and we are summing them up for all the n data points. Does it look familiar?
Expectation, sir.
Yeah, it is the expectation. Okay. So in the expectation, how you do, you multiply the probability for the random variable value and you sum them up for the all the n data points. Okay. And that's what turns into the expectation part. Okay. So in the algorithm, the expectation maximization algorithm, the expectation part is coming from here. Okay. So that's what I have written here. Okay. Is this part clear to everyone? Yeah. Yeah. Any doubt, anyone till now? So this is just one table to summarize. Okay. So the lambdas that we have introduced here, the new variable, okay, this will satisfy the following relationship. That if you pick any data point, okay, lambda ik basically denotes the probability that the ith data point is coming from the kth cluster. Okay, it is that conditional probability. That given you have the ith data point, what is the probability that it will come from the cluster k? That's what it is mean by this lambda ik denotes. Okay, and therefore, if you fix any ith data point, the probability that it will come from the cluster 1 plus cluster 2 plus cluster 3. Okay, this will sum up to 1. So for example, if you pick the first data point, the probability that it is coming from the cluster 1 plus the probability it is coming from the cluster 2 plus the probability it is coming from the cluster 3. Okay, this will sum up to 1. Okay, this will sum up to 1. This will sum up to 1. This will sum up to 1. Notice this will not sum up to 1. Okay, if you see the question sometimes, okay, instead of k equal to 1 to k, what they put in the summation is I equal to 1 to n. That is, they sum up like this. Okay, that is the probability like of choosing the data point from one cluster. Okay, so they sum up like this. This will not sum up to 1. Okay, this is the probability that lambda ik denotes. Okay, I here means the data point, k here means the cluster, sorry, the component. Okay, is this part clear? Okay, maybe em, yeah. So we will now formally move towards the em algorithm part. Okay, the algorithm we will use to estimate the parameter for our Gaussian mixture model. Okay, so we will use uh, this em algorithm. Okay, so as this line says, this algorithm makes use of some intermediate variable that helps us in the parameter estimation, and that is, we call it as the lambda ik. Okay, that is the conditional probability that given you have seen your ith data point, what is the probability it is coming from the cluster k for the component k. Okay, I corresponds to the index of the data point, k corresponds to the index of the component. So lambda I can be interpreted as the conditional probability. Okay, and as it is a probability, it will lie between 0 and 1. And for the ith data point, if you sum up the probability of this ith data point coming from all the clusters or the component, okay, it will sum up to 1. And there would be kn such variable, because for each data point and each component, you will have one lambda ik value. Okay, So there are k components and n data points. So these lambda ik would be total k times n. Okay. And again, we will collectively refer our all the
Yes, sir. Sir, you are not audible.
hello everyone. Am I audible?
Yes,
Yes, sir, you are audible.
Okay. Sorry for the disturbance. Just confirm whether you are able to see my screen. Are
Yes,
you
sir,
able to see?
basically.
yes.
Okay. So around what time did I disconnect? Or like last till how much were you able to listen to me? Till what part?
You can start from this, which is, uh, yeah,
Till
points
here.
two and what.
Okay.
And here.
So did I explain how there are k and such variables? As
You
for
can explain
each,
once again.
Yes, sir, this is key.
I will just again I will just start maybe from EM. Okay. So EM algorithm, that is expectation maximization algorithm, is the way that we will use to solve for the parameter problem for the GMM. Okay, as it does not have a closed form solution. Okay, unlike the MLE that we did for Bernoulli or Gaussian. Okay, they have the closed form solution, but unlike those, it does not have a closed form solution. So we use an iterative approach for the EM algorithm. Okay, and this algorithm makes use of some intermediate variable, that is this lambda ik, which actually denotes the conditional probability of the ith data point coming from the kth component. Okay, given that you have this xi data point, what is the probability that it is coming from the cluster or component k? And as it is a probability, it will lie between 0 and 1. And if you sum across the probability of the ith data point coming from all the component, that is from first component, second component, okay, it will sum up to 1. And as for each ith data point and k cluster, there would be one lambda ik value. So there are as k component and n data point, so there would be k n such variable, that is this. Okay. And
Sir, this lambda is,
Mhm.
it is giving which probability, sir?
It is a conditional probability that given you have
Eh,
seen the data point, what is the probability it is coming from the cluster K? Okay. It is a conditional probability that given you have seen the data point xi, what is the probability that it is coming from the cluster K? So it is denoting like f z given x. Okay. So it is this probability.
Sir, what is the difference between pi i's and lambda i's, sir?
Okay, pi I is the probability of only choosing the class component. Okay, that is the prior probability, and it is just the probability of choosing the one component. While lambda ik is the conditional probability of of you have given the data point. What is the probability now that as you have seen the data point now, it is coming from the cluster K or cluster 1, cluster 2 like that. Okay.
Okay,
Basically,
sir.
what
Thank
we have seen above here, maybe where this part that we were doing here. Okay, that is what is the probability that negative 0.1 is coming from the cluster 1. Okay, this what denoted by lambda ik. Okay, this conditional probability. This what lambda ik represent. Okay,
you. Okay, sir.
anyone any more doubt? No. So first of all, again, we will be collectively referring all our parameters as theta. Okay, and there are two steps in the EM algorithm. One is E, one is M step. Okay, E stands for expectation, M stands for maximization. Okay, in the E step, we update the value of the lambda. Okay, using the current value of theta. Theta means this all the parameters we are referring as theta. And in the M step, we update the value of theta using the newly found values of lambda. So in the lecture, professor did what? Uh, he says something like this: you fix the lambda, you fix the theta, okay, and estimate on lambda. Then you will fix your lambda and you will estimate on theta or maximize your theta. Okay, so that's what these two steps mean. Okay. Now the procedure, first you will initialize. Okay, so theta naught. Okay, the theta superscript 0. Okay, this means we are initializing all our mu. Okay, we have k means, k variances, and k prior probability. Okay, this we will initialize them. And if you are in some iteration t, okay, it will look like this. This is the for the initialization, and at some iteration t, this would be like your mu, sigma square, and prior probability. Okay, I hope the notation clear to everyone. And as it is a iterative algorithm, there should be two things: either it will converge automatically, or you have to set some what we say criteria to get it converge. So unlike k means, okay, if in k means it will converge. If you look keep going, the k means algorithm will converge. Here you pick one convergence criteria that in the theta t plus 1 minus theta t. This means the parameters that you got, okay, in the next iteration and in the before iteration, previous iteration, okay, the difference between them, okay, what this will represent, this symbol, that is the distance square. Okay, so that if it is less than some epsilon, Okay, this will be like threshold that you will set. Okay, so that it can be like 10 power minus 3, 10 power minus 5. Usually we set it like this. Okay, so if the difference between those two are less than this much, then we will call our algorithm that it got converged. Okay,
Sir,
that's
can you please show how this norm will look like? Because theta is the parameter of three things. So will
yes,
it be a vector or
yeah, it
what?
will be a vector. Okay, in the programming assignment we will be solving this. So how theta 0 we will use? It will be a vector like mu1 0. Okay, mu2 0. Okay, till mu k 0. Then we will use sigma 1 square 0, sigma 2 square 0. Okay, like sigma k square 0, and then comes the prior probabilities, that is pi 1
Okay.
pi. Okay, till pi k.
All these parameters together will make one vector, right, sir?
This would be one your theta naught. Okay, like it will, the first k value in this theta naught would be your mu, the next k would be your variances, and the next k are the prior probabilities. Okay, and that would denote your theta. It would be a vector. So what would be the length of this vector? It would be 3k, right? The number of component times 3. Okay, and if the difference between the theta t plus 1 minus theta t, that is the parameter that you got in some iteration t plus 1 and the before iteration t, if the difference between them, okay, is less than some quantity that you will decide by yourself, okay, then you will call the algorithm converts. Okay, now what do you have to do until it got converged? So this is like the full process. Okay, that until it get converged, you will keep doing these two steps, E step and M step. So in the E step, as we talk about, we will update the value of lambda ik. Okay, that is the conditional probability. Okay, it is the contribution of the kth component to the point xi, that given that we have observed the point xi, okay, what is the contribution of the kth component to it? Okay, and it also we can say that represents the posterior probability of z given x. Okay, and again the Bayes theorem, we have seen this now multiple times. Okay, this lambda ik is the prior probability times the normal, okay, divided by the density of GMM, and in other words we can write it like this. Okay, so this conditional probability that we have seen before is denoted by lambda ik. Okay, and this is the E step. Is it clear to everyone? So what we were doing before was the calculating the lambda ik values. Okay, is the E step clear? That's all there in E step. If it is clear, then we will move towards M step. Okay, now the M step, what we will do, we will use the lambda ik value that we got before in the step to update the values of our pi k, mu k, and sigma square k. And that's how they will represent. So if the equation is not clear how they are looking, then what Prof said was mu k is nothing but is the weighted average of the data point, right? And they are weighted by this lambda ik probability. So mu k is the weighted average. Again, variance is also like some kind of weighted average, okay, because they are also multiplying. If we remove just these sigma ik, lambda ik, sorry, if you remove these lambda ik here, then what it will become? It will be just like your sample mean and sample variance, and that are what, like, that are the estimation for the your normal distribution, right? If you perform MLU normal distribution, the parameter that you will get for mu and sigma square was sample mean and sample variance, and in the GMM it is just the weighted average. Okay, it is again also what we say the sample mean in some sense, but it is now weighted average and weighted by the conditional density expansion. Okay. And same for the variance.
This denominator part, sir.
For mu k? Yeah.
Yes. This
Yes.
will be summation of probability of those points which are coming from the cluster K. That only.
Yeah. We will fix the cluster k and we will sum up for all the n data points. Okay. And
Which
that
are
would be
coming
your
from that cluster
yes.
K only.
Yeah. Okay. So that's how we will calculate the mean. Okay. For the if you are updating the mean for one component k, okay, you will choose the conditional density function. Okay, that what is the probability that this ith data point is coming from the this cluster k. Okay, and you will do this for all the n data points, sum them up. Okay, and that would be your denominator. In the numerator, you will also multiply it with the data point. Okay, so that's how it is weighted average, because you are weighting your data point with this probability. Okay, and it is kind of weighted variance. Okay, because again you are weighted them. And pi k is simple. It is just like normal, like kind of you can understand it as a mean of the probabilities. Okay, like what is the probability that if this ith data point is coming from the cluster k? You fix your component k, and for all the data points, you will sum those probabilities divided by n. Is the m step clear? I know these things might be a little bit hard if when you will like first time you will see this, okay? And mostly we won't be asking more derivation type question from this. So at least try to remember the formulas, okay? These formulas, okay? This formula for lambda ik, how you calculate those probabilities, okay? At least try to remember those and what the notation means, okay? Even if you are able to understand that much, that is also good. In first go, maybe you will not be able to understand everything, but slowly you will. Okay. So till EM step, anybody has any problem in the M step? No. Okay. So this is the like last page for today slide. Okay. That is, we will see side by side our EM algorithm and K-means algorithm. Okay, and how they are similar. Okay. So there are only two steps in EM algorithm, that is the E step and M step. E step denotes the probability that the ith data point is coming from the kth cluster. Okay. This E step in K-means is similar to the reassignment step in K-means. Okay. The only difference is here we are going in a soft manner. Okay. So what we are doing here in each step, that if you let's say you have a data point X, okay, and you have only three component K, okay, you have only three component and you have your data point X. What you will get in each step is that the probability that it is coming from the cluster component 1 is, let's say, some 0.7, from cluster 2 it is 0.2, and from cluster from component 3 it is 0.1. Okay, that's the story for EM. Okay, and that's what you do in E step. While in K means this is similar to the reassignment step, but here we are going in a hard manner, that either it would belongs to the one component or one cluster, or it will not belongs to that cluster. Okay, here the lambda ik value can only take whether 1 or 0, while here it will take any value between 0 and 1. Okay, is the first part clear? E step and reassignment step between EM and K means. In K means we are going in a hard manner. Okay, that is either the data point will belongs to that component or it will not. while in each step we have given them probabilities that like 0.7 for first component, the probability for it will belongs to the second component is 0.2, and for third it is 0.1. While in reassignment step in k-means, it will be either 1 or 0. So like either it will belongs to one cluster or it will not belongs to that cluster. So like 0, 1, 0, that means the x belongs to the second cluster, like that. Okay. The m step in EM algorithm is same as the computed mean or recalculating your cluster centered. Now, is the equation or the expression that I have written here makes sense based on the lambda ik values here? Does this expression is exactly same as how you calculate the cluster centered for your k-means? Or are you all able to understand here? Okay, no. So how you calculate the mean of the or how you will update the mean in the k-means? You will take all the data points that belongs to that cluster k, okay, and take the mean, right? So here, if you see what we are doing, we are multiplying all data points, that is from I equal to 1 to n, with this lambda ik, and divided also by the same, the summation from lambda ik from I equal to 1 to. But if you see here, the lambda ik can only take two values. Either it will take 1 or 0. And when it will be 1, it will be 1 when the data point, ith data point will belongs to that cluster. And for all other, it would be 0. So the numerator here will give us the sum of all the data points that belongs to that cluster k, because for all others, it would be just 0 times that. And here it would be just the number of the data points that belongs to the cluster k. Yes, so there any doubt?
No, sir. Clear.
Yeah. Okay. So that's why the m step is similar to the cluster update step in k-means. Okay. So is the comparison between EM algorithm and k-means clear to all of you? Okay. The only thing is in EM algorithm, we are going in a soft manner because we have introduced the probability, while in k-means, we are going in a hard manner. Okay. That is either it will be 1 or 0. And some final points about EM. Okay. And that is, so if you have seen, what we are trying to maximize in the EM algorithm is the modified log likelihood function, right? Okay. Because our original likelihood function was this, but we are using this likelihood. Okay. That is the modified form. Okay. So under there are certain proofs about this. Okay. And that those proofs we will not be discussing in our course, but according to those proofs, under certain conditions, okay, that Jensen inequality we talked about will become the equality in the E step. Okay, so when you do E step, you update your lambda ik, okay, and that will make your inequality that we had between log likelihood, original log likelihood and modified log likelihood, okay, that inequality would become equality. Okay, so it's kind of like it. If the original log likelihood curve is going like this, okay, and the modified log likelihood curve is going like this, in the E step, it will touch the original log likelihood, okay, and then you will perform your M step to maximize your parameter, because now you are in original likelihood scenario. Okay, and that's how this works. Okay, we will not be going into the proof of how this inequality becomes equality. Okay, that's not in our course mainly. And another point about EM is EM algorithm is soft clustering and K-means is hard clustering. That's what we shown here before. Okay, as EM algorithm, we take values between 0 and 1, that is probability. While in K-means we do hard clustering, that is either the data point will belongs to one cluster or either it will not. Okay, and EM algorithm converts to K-means. Okay, so by that, if you just keep on running EM algorithm, it will converge to K-means. That one here. Okay, so that's the end of the presentation. That's all I had for today. Anybody has any doubt in whatever concept that we discussed today? Okay. Okay, good. So now we will move towards the programming assignment part. Okay. I will suggest you all to maybe go through the document after I will share it with you. Okay. So again, to get hold of the concept again. And there's those probability that I told you to calculate, try calculating them. Okay. In the PDF that I will upload, it will have the original answer. Okay. What the answer would be. Try calculating them. And tomorrow is also the instructor session. Maybe instructor will also discuss the same part, GMM and EM. Okay. So you can again attend that session also to uh, get a good understanding of these two concepts. Okay. So should we start with the programming assignment? Is everybody here ready for that? Okay. So we'll discuss first the programming assignment. There are two programming assignment in this week. Okay. So we'll start with the first one. Maybe you guys can also open the programming assignment side by side. Okay. From your portal. I'll share my screen in few minutes. Okay, so is my screen visible? Can anybody confirm? Okay. So I hope you can work along with me on side by side. Okay. So first of all, you need to go to this file tab. Okay, and click on save a copy in drive. Okay. Now, while clicking on this, it will create a copy in your drive. Okay. So start editing on that copy. Okay. Don't start on this one. Otherwise, the changes that you will make, okay, will not get saved. So just a minute. So should we start now? If everybody has saved the copy or created the copy of the programming assignment part 1. Okay.
Sir, where can we find this? I'm sorry.
Okay, this assignment, if you like,
Master.
go. No. Just open your week 4. Okay, I hope my portal is visible.
Okay, okay, got it. Got it.
Okay,
Okay.
scroll down. In the end, you will find this
Okay.
programming assignment 1 and 2. Click on this link, and it will open.
Okay, sir. Thank you.
Then you have to create a copy. Okay, don't start editing in this file, otherwise the changes that you will make will not get saved.
Okay.
So I will wait for 1 minute for everyone to create the copy, and after that I will start. Okay, so let's start now. Okay, the first thing you need to do is to connect. Okay, click on the connect icon here. Okay, this will connect your collab file to the Python backend engine. Okay, that's stored in the cloud. Okay, now that's the way to connect your collab. And even if you don't do this and directly run the cell, okay, it will first connect and then run the code. Okay, so the first uh, code cell that is we have given here. Okay, in this, what we are first doing is we are importing the numpy. Okay, that is the numerical Python package as NP. So the as here denotes the alias. Okay, that is the shortcut keyword that we will be using. Okay, to refer to NPy, sorry, numpy. Okay, because every time writing numpy, the whole word, okay, it's messy. So we use this shortcut keyword NP. Okay, so to refer the numpy package. And another package that we required for this assignment is matplotlib.pyplot. Okay, that is the library we will use for plotting our graph. Okay, so these two line, I hope it is clear. The next two line of this code, okay, it basically changing the figure size of the matplot library. Okay, so by default the figure size, if you plot any figure in mat using matplotlib, okay, by default I guess it is some 6 by 6 size. Okay, so here we are changing that size using this code. Okay, you don't need to do anything, add or remove any line of code in the first two in this cell. Okay, just directly run this. Okay, the sampling part now. Okay, this line, that is RNG equal to np.random dot default underscore RNG. Okay, this is the way in NumPy to randomly sampling. Okay, this is how you generate any random number in the NumPy. Okay, that's the way. Okay, you have to do. Okay, np.random dot default underscore RNG. Okay, now if you see in this line of code, well, this line, okay, the only difference that is there is we are putting one parameter, that is seed. Okay, so anybody knows what this seed value will do?
If we are selecting a certain random numbers, for example, then it will take the same random numbers all over.
Yeah. Okay, so when you set this seed value equal to something, okay, usually we have set it to some odd prime number type. Okay, 42, 131. Okay, these are the usual. Okay, so when you set this seed value equal to some number, okay, what will happen every time that when you will run your code cell, okay, it will give you the same sample, okay, every time in each run. So why this is useful? Suppose you are working in some group project and you are working for any project that you are creating, okay, any model that you are training. Okay, so you're choosing some random sampling. Okay, based on that you are working on your project. Okay, so if you are going with the random sampling, If you again run the cell, you will get a different set of samples, right? So usually if you run any or train any model, we want that sample data set to be stored or maybe remain as it was there in first run when we trained our model. Okay, so we often use set this seed value to some number. Okay, so that in every run, whenever we run the cell, we always get the same sampling. Okay.
Is it similar to random state, sir?
Yeah, similar to random state. Okay, that is also the same thing. Okay. Now we have stored this np.random.default_rng with seed equal to 101 in this rng variable. Okay. Now if I just comment this, okay, and click on rng, okay, and then okay, maybe dot. Now you will see it will give me suggestions like this. Okay, so if you want to sample the data from, let's say, okay, are you able to see the suggestion?
Yes, sir.
Yes, sir, it is giving distributions.
Yeah, okay. I hope. So these are giving these suggestions like beta, binomial, okay, chi-square, okay, then exponential, then we will have hypergeometric, okay, we will have normal also, multivariate normal, okay, this is the normal, okay, Poisson, okay, random, okay. So we can use these, okay, any of them to sample our data points. Okay, so if you just want any random number, then you can just put rng.random and it will give you a random number. Okay, if you want to sample from a normal distribution, you will do rng.normal and it will take the parameter like mu and variance. Okay, and just pass on these and that will sample your data point from the normal distribution. Okay, so that's how we
Sir,
sample. Yes.
regarding this seed, sir,
Hmm.
seed is equal to 1 not 1.
Hmm. Yes.
So what is this? Means these many samples will pick from this.
No. As I told, the seed, okay, this seed number, okay, it is just a particular number. It is not necessary to be 1001. You can give any number, okay, 42, 32, 100, okay. It's just that it is some kind of like, let's say, identity, okay. And what seed will do, okay, it will, every time you will run the cell, okay, it will give you the same sample data point, okay. While if you don't give the seed number, okay, just like in previous cell here, okay, in previous cell here we have not given the seed value, and now if you do rng dot random, okay, okay, what's spelling there, okay, it will give you this number, okay, 0.91 0.917. Now if I again run, it is giving me different number, right? Now if I put the seed value equal to 42 and now run this cell, it is giving me point, just note down this number, and now if I again run, it is giving me the same number, right? So that's what seed will do. Every time you will run the cell, you will get the same sample data point that you got in the starting. Got it?
Okay, sir. Thank you.
So maybe I will just comment it. Seed will give us data point in each run. Okay. So here they are, what they are doing. They are sampling an integer, okay, between 0 and 2 of the size 10. Okay. Now again, it will run like Python for loop. Okay. That means the 2 will not included. So only 0 and 1. Okay. So it is sampling number between 0 and 1. And what we want size 10. Size 10 means we will sample 10 points between 0 with 0 or 1. Not between 0 and 1, either 0 or 1. Okay. So it is kind of like Bernoulli. Okay. So it is sampled like this. Okay, this code cell was just to illustrate you how the random sampling works in NumPy. Okay, and what is mean by seed value. Now we will come to the point on what we say, the problem 1. The problem 1 says, for a data set X given below, okay, what is the MLE of the mean if we use Bernoulli distribution with parameter P to model this data? Okay, perform all the operation in the given cell and do not change the seed value. This part is important. Don't try changing the seed value in any of the tab or any of the cell below. Okay, otherwise you will get a different answer that will not match with the answer given in the portal. Okay, just don't change these. So what we are doing, again, we are using our RNG equal to np.random.default RNG, okay, with seed value this. Then we are doing RNG.integer with 0, 2 for means it will either take 0 or 1, and we are sampling the 1000 data point. Here this size means the number of data points. What we have to calculate is the MLE for the Bernoulli distribution. What is the MLE for Bernoulli distribution? What is the MLE for Bernoulli distribution?
Mean.
Yeah, sample mean, right? Okay, so this is the sample data that we got. So all we need to do is basically just find the mean. Okay, so okay, just go back to the previous code cell. Okay, when you are sampling only 10 data points, okay, when you only want the 10 sample, it will give you this array, which is a numpy array. Okay, so here also you will get a numpy array of 1000. Okay, and how you find the mean of a numpy array? If you want to find the mean, how you will do it?
np.mean.
Yeah, np.mean also you can use, or maybe directly you can put down the vector, okay, or the array for which you want to find, and just do this x.mean. Okay, because x is the uh, array, numpy array that for which you want to find the mean, and you can also directly do this. Use what you said were also right. np.mean, in that you have to pass the argument x. Okay, they both are equivalent. Okay, so if you run the cell, you'll get mean value to be 0.506. Okay, that is the answer for your first question. Now, just one thing that here it tells that what happens if we increase the size of the data set to how much zeros are there? 1, 2, 3, 4. Okay, for 10,000, we see that np.integer is only giving us observation from a discrete uniform distribution. Okay, in other words, if you think about a coin toss, the coin is unbiased. So that means it is giving basis on the uniform random sampling. Okay, so if you toss a coin which is unbiased, so it is this RNG.integer that we were choosing here before. Okay, it is working like that. Okay, so here they are introducing another way to sample the data point. Okay, in which we can go within some bias form. Okay, how do we generate the biased coin? Okay, that is where p not equal to 0.5. Okay, so that's where this choice method comes. So this rng.choice. Okay, so that's where we will use this rng.choice. Okay, so in this rng.choice, we give what it will take here first is the array. Okay, so this array will contains the basically the number that you want to sample. If you want 3, let's say 0, 1, 2, so what you will do, you will just add 2 here also. Okay, then it will sample either 0, either it will choose 0 or 1 or 2. Okay, the next argument is size, that is same as before. This is the new argument that it will take, that's p. Any guesses what does this p will represent? What will this p represent? Any guess?
Probability, sir?
Yeah, okay. So this p will represent the probability, okay, and how they are like kind of index manner sense. So this 0.2 will denote the probability for the sampling of the 0. This 0.8 will denote the probability for 1, and as I have added 2, so I have to make some changes here. And let's say 4, and if I, okay, 4 to 6, so next is also 4. Okay, so maybe let's say use for different. Okay, so now what? 0.2 denotes the probability for choosing 0, 0.3 denotes the probability for choosing 1, and 0.5 denotes the probability for choosing 2. Again, just focus that it should sum up to 1. Okay, now if I will run this cell, okay, we will see we got these three values, okay, 2, 1, and 0, okay, based on this probability distribution type. Okay, is the choice method clear to everyone? But okay, here also the note is given that the array P specifies the probability of 0 and 1. Okay, and it should sum up to 1. Next is our problem that sample 1000 points from a Bernoulli distribution whose parameter P is 0.7. The P is 0.7 means it is the probability of head, that is x equal to 1. And then compute the MLE of the parameter given the sample. Okay. Okay. If one note is given to you that it may seem the pointless to compute the MLE when the parameter is already known to us, but it would be a good exercise for you for the understanding of the concept with the toy data set. Okay. So we have to first create our data set. Okay. Like rnz dot choice. Okay. What would be the first argument it will take? It will take the array of the values that you want. Okay. The Bernoulli distribution take only two value, 0 or 1. So we want either 0 or 1. Then you have to mention the size. Okay. You want 1000 data points, so 1000. The next argument was the probability. Okay. So what should I enter in the probability? What is the value?
0.37.
Yeah. Okay. 0.3 comma 0.7. Okay, because we have given the probability was 0.7 for the head, for 0.7 by indexing you will go. Okay. So we have sampled. Now what we have to do next is we have to calculate the MLE on this. So that is just the mean. So that is x dot mean. Run the cell and you will get this as your MLE. Okay. The shortcut for running the cell is control plus enter. Okay. Anybody has any doubt in the problem 2? No? Okay, let's move to our plot problem 3. Okay, here we have to plot things. Okay, so you have to plot the bar graph of the above sample. Okay, you can use plt.bar for this. Now, Colab provides a very good way. Okay, sometimes what will you do? You will forget like how some function or some argument works. So what you can do? You can put.
Can you please scroll up previous problems? I'm not getting it.
Yes, this part.
Yes.
First, we are using the choice method that we discussed. As the Bernoulli will take only two values, 0 or 1. So that's what we have given them as the array. Okay. Then the size. Okay. And then the probability based on that. Okay. Clear? And then the next the MLE, that is just the mean. Any doubt? If not, then we will move to the problem 3. So what we were discussing is we have to plot the bar graph. But suppose let's say you don't know how you can use this plt.bar method. So Colab provides a very good way that hello, am I audible?
Yes, sir.
Okay, just give me. I will just present again. Okay, so you can put question mark at the end. Okay, it is not just for only for the plt.bar. Okay, for any function that you don't know how to use in Colab, okay, you can just put question mark at the end of that. Okay, and then just run the cell. What it will do, it will open a help document for you. It will have which will have all the information about the function. Okay, like what argument it will take, height, width. Okay, as it is showing that this will take x height. Okay, next it is also talking about the parameters. Okay, what does they represent? Okay, you can read this document. Okay, to get a better understanding. It is given that x is a float or array like. Okay, height of the bars, width of the bars. Okay, and then there's more alignment. Okay, so there are more parameters like colors. Okay, so you can get all such of info by just putting the question mark at the end, and you will get all the info about what does function do. Okay, and it is very useful because there are so many things. Not nobody can remember everything. So that's one practice that you should follow. At least you should have a one idea like what function you have to use. The rest thing you can just put question mark at the end and get the type of info that you want. Okay, so what this we will be using is we will first pass the array. Okay, the array that we want was 0, 1. Okay, and the next thing it will take is you will say what we say is the height. Okay, when we open the help document, okay, let me open this side by side. Okay, so that it is clear. Now, plt.bar. So first thing, if you see that it is asking is the array. Okay, so what we have is 0, 1. Okay, next is the height. Okay, how much height should it go? So how much height they should go from our x that we calculated here. Okay, we will try to find the number of zeros and one that are there in this x that we have sampled. Okay, and either you can do a for loop and iterate through that also. There's another way to do this, and that is what we will be doing here is because it will take an array form. Okay, like this. What I will be doing here is I have taken this x and put this condition inside this x. Is this part make sense? Okay, this you can only do in NumPy. Okay, this supports by NumPy. So what it is doing is this is kind of like list indexing, but you can put condition inside the list indexing also here. So this will take the array. Okay, this will give you the array where the x element of the x are 0. Okay, this will only give you the array. And similarly also here, this will give you the array where the elements of the x are 1. Okay, because you have put the condition x equal to 1. Is it clear, this condition part, how this works? If I show you as an example, okay, let's say you have an NumPy array 1, 1, 1, 2, 2, 2. Okay, now if I do x equal x and equal to 2. Okay, now notice it from the x array here. Okay, it has sampled only those points where our value is 2. Okay, so let's comment this. But if you notice, what we want here is not the array. What we want here is a height. But height by that means is the number of 0 in our sample data point sample data set X and number of 1. So we have to use here dot size. Okay, and same here also dot size. Okay, so the size method, okay, gives us the number of data points in that array. Okay. So this first x equal to 0 will give us the array of all the zeros that are there in our data set. Okay, and this dot size will give us the number. Okay. So I hope this part is clear. Anybody has any doubt? Okay, good. The next it will take is the width. Okay. Now if you see this this given here, width equal to 0.8. Okay. So this is the by default width that it will take. Okay. But if you want a different width, you can just put, let's say I would just want the 0.4. Okay, you can put that 0.4. By default, it will take this width. Okay. Now there another parameter that we see here, that was the color. Okay, that we will give color at the end, but first just run this cell. Okay, let's comment this and run the cell. Now, one thing that I want you all to notice, that I run this cell here. Okay, that also has the same variable name X. Okay, and also before also we are referring to the same X. So what do you think the collab will, which X this collab will refer to if I run this cell? Is it this one or the previous one?
The latest one.
Yeah, okay. So this thing you should be careful, okay, while working with the collab. Okay, if you put the same variable name, it will take the latest one which you have run. Okay. So because I want the previous one, so I have to rerun this cell now. Now this is the latest variable. Okay, this is the latest value that it will take. Okay. So now if I just run this cell, I hope it don't give any error. Okay, this cell created this bar graph. Okay, if you are not able to see, okay, this is the bar graph that it will look. Okay, I hope it is clear. Now, as we were talking about the color, okay, so as it also take another argument, color, so it is an optional. You can pass the color, but I will just show you how you can, if you want to color. Okay, so what I want, I have to pass two color. The first one I will pass as blue. The second one I will pass as orange. So that means what it will do, it will color the first bar as blue, and as it is already blue. Okay, and it will color the second bar as orange. So just run this, and now you can see one is blue and one is orange. Okay, if you want to color it, it's optional. And there are many other things that you can do. One is what we say is label. Okay, labeling is important. So you want to label your, let's say, the y-axis. Okay, what does the y-axis represent? It represents the frequency, right? So there's this function in the PLT, okay, that is y label. Label. And in which you can just type the frequency, frequency of 0 and 1. Okay. I run this, just see this. Okay. Here it is given this label. Okay. And there's more, you can decorate it as plt.title. Okay. That is bar graph of Bernoulli sample data set. Okay. So it will give this title to this graph. Okay. It is a small decorating I'm doing. Okay. Nothing new. Okay. So I hope this bar chart, bar graph creation is clear to everyone, how you create the bar graph.
Sir, if we don't mention the widths, then what difference will it make?
It will take the default value. This, okay. You've seen the width has changed, okay. The default value, if you open this, okay, it has taken the default value 0.8.
Okay, sir. So the answer,
No.
interpretation from it won't vary.
Yeah, it won't vary. It is just it will give you a different width. Okay, that's all.
Okay.
It might be useful when you have more bars. Okay. Otherwise, because the graph would become very wide. Okay, if you have more bar that you want to represent, then maybe you want them to be a smaller width. Okay. Here it doesn't matter. The interpretation would be same.
Okay.
Okay. So I will just go back to this. Okay. Now the problem 4. What is the impact of the size of the dataset on the MLE? Okay. So across these different n, that is 10, 100, 1000, 10,000, lakh, 10 lakh, like that, we will sample each data set from Bernoulli distribution with this parameter. For each data set, we'll first compute the MLE and then compute the difference, or that is the absolute value, between the MLE and the true parameter. Okay, that is this. That is, let's say first you started with the 10. Okay, we'll sample 10 Bernoulli distribution data point with p equal to 0.2. Okay, this is your original, and then you will use your MLE, that is your sample mean, and take the absolute difference between them, and that is would be D10. Okay, and that's how you will do for your all these data points. What question asks us is to plot Dn with respect to n. So this is the question of understanding how your what we say, what effect it will have when we will increase the number of samples. Okay, and what you expect in general, what kind of expected behavior you expected, what is the behavior that you expect, what will happen when you take more and more sample from your data set, what will this value reach? Basically we will get closer and closer to the original mean type. Okay, so when you will sample more and more data points, okay, this difference will keep decreasing. Okay, let's see it through Python. Okay, first what I will do, I will create a size array. Okay, that is, it will contain all these n values. Okay, so 10, 100, 1000, 1, 0, 4, 10,000. And how many we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. So I created this size array. Now the next thing I will create is diff, an empty list. Okay. What it will store? It will store this difference. Okay. Across each size, we will store this difference value between the original and the MLE that we will calculate. We will store that difference in this difference list. So let's say for size and size array. Okay, so this will give me each size. I will do rng.choice. Okay, that is the way to sample 0, 1, and size is equal to size is 0.8, 0.2. Okay, again, just focus. This 0.2 is the probability for selecting one. Size equal to size means this will take the size. Okay, 10, 100. Size 10, 100. It will go like. We are creating our data point. Now we have created our data set. Next thing is to calculate the MLE. So MLE is x dot mean. Okay. After calculating MLE, what we have to do? We have to calculate this difference, that is MLE minus 0.2. Okay, that was this parameter. We'll calculate this difference and we will take the absolute value of that, because that's what it is asked here, absolute value. And we will append this difference in this diff array. Okay, so that is diff dot append. Okay, is this clear how this loop is working?
Yes.
It's a simple Python loop. Run it. Now if you see this diff, okay, see how the values keep decreasing. Okay, as you will sample more and more, the value will keep on decreasing. Okay, why? Okay, why it's get increased here? I hope we haven't made any mistake. Okay, we'll see why it's happening. But okay, usually that's the pattern that it will follow, that as you increase the number of data points, the value will keep on decreasing. Okay. Now next thing that we have to do is plot. Okay. So let's try plotting that and verify that. So to plot that, we will use this plt.plot. Okay.
Sir, what is the answer for the prior one?
This one, these are free. These are the graph.
No, sir, not this one. After this, where we had these six. Yes, for this one.
Okay, this is again the plotting question. Okay, we are yet to plot. This is again only the, you have to basically plot the dn and the n. Okay, this value that you will get with respect to this. So we are coming to that now. Till now we just calculate the diff. Okay.
But sir, there was something about the size, right? This
No.
MLE X don't mean.
No, what it is telling that for each data set, first compute the MLE and compute the difference between them. Okay, MLE and the true parameter. That's what we are doing. And that what it is saying, that plot dn with respect to n. What do you observe? Okay, so it is just again observation, not any
Okay, sir,
numerical answer.
can you please show this 26 port cell?
Okay, this.
Yes, sir, this one. Yes, sir, this one.
Okay, so we have created the size array, whatever the sizes that was given to us. Created one empty list diff. We are iterating through all the values in this size array. Okay, and then we are sampling our number of data points. We have given this size equal to size. Okay, this size is this. Okay, this size here is the variable that refers to this. While this size here is the argument. Okay, so we have sampled our data point. Now we will use MLE to calculate the mean. And then we will calculating the difference of the MLE and the 0.2 that was original. Okay, taking the absolute value of that and appending it to the DF here.
Okay, sir. Thank you.
Now we will plot this diff.
Sir, is the last value larger than the second last value because
Yeah,
of
that's
that
what,
abs?
that's what I am also saying.
Might have gone
Usually,
to negative.
that's what technically it should not happen. Let's see what is happening. Okay, let's try plotting the graph. Okay.
In the graph also it's showing a little slanted towards up. Okay, sir.
Okay. Let's try first plotting. Okay. So plt.plot, it will like first it will take the x value. Okay. So what you want on your denominator? Oh, sorry, not denominator, x-axis. Okay. So we'll put this size array in the denominator. Sorry, not in denominator, in the x-axis. Okay. And see, this has also opened in suggestion that it plot y versus x. Okay. So in the x-axis, I have taken size array. On y also, we have taken this diff. I will use something called as line style. Okay. So this line style basically, instead of just a bold line, okay, it will create a dot 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 line. Type that. Okay. Now we have to do one thing here. Okay, let's first just plot this. Maybe after that it will be better. So if you just directly plot this, okay, it will look like something like this. Okay, but you are not. If we open it in view screen, okay, but this is not very good to see. Okay, now the reason is because the scaling is very much different. Okay, between the x-axis and the y-axis. So we will change the scaling part for the x-axis. Okay, and the way to change your x-axis scale is using plt.x scale, and we will use the logarithm scale. And with that, if you are going to run, you will get this kind of graph. Okay. Now you can easily identify this. Okay. Now there's something that we can do, that is extract that. There's something called as marker. Okay. Now you will see what it will do when I run the cell. Okay. What it will do, it will point these values also here. Okay. So now it is the last value we were getting some a little bit higher. Okay. So I don't know why it is going higher. It should not go. Maybe we will come up to this in the end. Why this last value becoming more than the previous one. Okay. But for now, is the graphing part clear to everyone? How you are sampling from n different uh, sizes and then plotting this. Is it
Sir,
all?
how the scale was changed, sir? Please, can you show once?
This plt.x scale. Okay, just pass the function name. If you want to change the y scale, just change this x to y. Okay. If you hover over it, it will also give you the suggestion. Okay, like how it takes linear, log, uh, more. Okay. Okay. So just give me 1 minute. I will reshare. Let's move to our point, problem 5. Okay. Problem 5 says sample.
Sir, can you please show the code again for the plot?
Okay. I will share this collab file also with you. Okay, at the end. So.
But sir, please give me a minute. I am just there's one part that I have to write.
Yeah.
Marker.
This marker basically will mark your point. Okay.
These dot
Yeah. This
in the
this this one dot. Okay. These are the marker. So it will mark your point where this value is lying. It is easy to visualize in that case, right?
yes, sir.
Otherwise, before
Okay,
it was
sir.
this
Sir,
lines.
in our programming assignment, we have
Hmm.
to type 0, right, for all these plotting questions.
Yeah. For all these plotting question, not in the programming assignment. If even if you try to give MLT or PP, and there's any plotting question, you will type 0. Okay. In
Okay,
there.
sir. Thank you.
But of course, there they ask for the collab file also in the MLT or PP. So they will check your code, how you plot that. Okay. The problem 5, sample 1000 data points from a 6-sided bias die with faces this. Okay. Before we were only sampling 2, now we will sample 6. And these are the parameter. Okay. This is the categorical distribution. And even though we have not covered the categorical distribution, like how to calculate the MLE, okay, but in the categorical also, it's also like the sample mean. Okay. and it just works in the same manner. Okay, we have one program, we have one practice assignment question. Okay, practice assignment has a similar problem where we need to calculate the MLE for a categorical distribution. Okay, so maybe if we discuss that problem, then we can discuss. Okay, but for now, the MLE for the categorical distribution is also similar to sample mean. Okay, so it's again the same problem that we have to sample 1, 2, 3, 4, 5, 6. Okay, with these probabilities, and then find the MLE for P3. P3 corresponds to third phase, that means this 3. Okay, so same thing, your X RNG dot choice, choice. Okay, this time I will pass 1, 2, 3, 4, 5, 6. Okay, the size is given to us as 1000. Then we have the probability array, and it is 0.1, 0.2, 0.3, 0.3, 0.05, 0.05. Okay, only change we did before and here, just we have increased the number of points that are sampling and their probabilities. Okay. Now we have to check what the MLE for P3. Now, can anybody tell me the code? How will you find the mean MLE here for P3? What code line will you write? How? What first you have to identify? You have to first identify the number of 3 that are there in your data set divided by the total number. Okay. So how will you do that? Or if you want hint, how I filtered my data set when I was plotting the bar graph for finding the number of 0 and 1. Try thinking about that. How will you do that now here for 3? Okay, let's go back if you don't remember. Okay.
So iterate over the array.
Iterate over array is one we can do, but we have this. We are using NumPy, so there is this functionality. Okay, this is the thing that I used here. Okay, to calculate the number of 0 and 1. Okay, that is you can. This is similar to list indexing, but in the indexing, instead of giving the number, you can give your condition on which you want to index over. Okay, so I have given the condition here, that is I want to sample, or I want all the points from all the elements from the X where X is 0. Okay, and then I've used this dot size, which will give me the length of this array. Okay, so here also we will do the same thing. You can do iteration also, just like run the for loop and count that. Okay, but as we have this, so we will use this. Okay, and dot size will give me the number of 3, and I have to divide this by X dot size. X dot size means again 1000. Okay, as there are 1000, so I can even put the
Sir,
1000
I haven't, sir, it's not clear to me why we are selecting 3.
because it is asking for the parameter P3, MLE for
Oh, okay.
P3.
Okay. Yes.
That's why.
So these probability, I think, do not sum to 1.
3, 3, 6 to 8, 9, and this will be 0.1. They are summing to.
Okay, so maybe I have made some mistake then, sir. Okay.
Okay, so it will sum to. Now, if I run this cell, okay, I will get this MLE 0.319. Now, let's say if I ask you to calculate the MLE for P5, the only thing that you need to do is just make this 3 to 5. Okay, and you will get the MLE for P5. Okay, so let's keep it like this. Next question, problem 6. Plot the bar
Sir,
graph
sir, can
for
you please show the
Yeah.
prior order x is equal to 3 dot size?
Okay. So maybe I guess today we will only able to cover the part 1. So maybe we will do the part 2 of this programming assignment in the next session. Okay. So let's quickly now what we have to do. We have to plot the bar graph of the above sample. Okay. So I will just copy paste my code. Okay, from the above problem to here. Okay. Something that I need to change is here is this color array. Okay, and the way I am doing here. Okay, it is here x equal to 1 and x equal to 2, and we have to do it for 6. So, maybe after 1, 2, 3. But, okay, maybe let's say just remove this. Okay, so I hope this code is clear. Okay. Oh, okay, one mistake. Not only 0, 1. It should be 1, comma 2, comma 3, 4, 5, and 6. Okay. So this is the value that bar will take, and how much height it should go. We have taken the number of 1s, number of 2, 3, 4, 5, and 6. Okay, and we have put them in one array. If you see this screen, and the width parameter. So parent. Oh, okay. This is the bar plot that you will see for this. Okay, same thing that we did before, except that we just increase uh, our points. Okay, the elements that we are taking. Before we have only 0 and 1. Now we have 6. Okay, but otherwise the code is almost the same. Clear to everyone? Okay. Now the problem 7. Consider the
Sir,
following
please
Gaussian.
give some 1 minute to allow us to actually complete this.
Okay. Okay, how much question will be have? 10. I hope till now anybody not have any problem in the coding part. Okay. This question clear to everyone. Should we move on now to next question? Okay. Now we will move to the Gaussian distribution. Till now we were only seeing the Bernoulli or categorical. Now comes the Gaussian. So consider the density of the 0.5. Compute the density of the 0.5 with respect to the distribution that is given here. Okay, that is mu is 3 and sigma square is 1.5 square. Okay. Okay, so this for this one direct method that you can do is you can import another library. Okay, that is called SciPy. Okay. So in the SciPy library, from SciPy dot stat or is it stats? Okay, we have this Okay. Input norm. Now it is 384. Okay. And you can directly pass these parameters to norm function. Okay. This is one way to do it. Okay. But we won't be using the SciPy here. Okay. So let's remove it. Even though we will be using SciPy library for week 10. Okay. Not now. So we have to manually compute it. For that, I will create the one function named Gaussian. Okay. It takes the parameter x, mu, and sigma. Okay. And what it will return? The value that we want. So this the density function is 1 by sigma 2 root 2 pi. Okay. So sigma into square root of np dot sqrt 2 pi. Okay. So the pi here is np dot pi into 2. Okay. So this was that 1 by square root of 2 pi into sigma. Okay. This whole maybe I can put the whole this everything. Okay. It will multiplied with np dot exp. Okay. Now it is again what? Minus x minus mu square by 2 sigma square, right? So how it we can write this as, now just tell me whether you are able to understand this or not. Minus 0.5 into x minus mu. Okay. X minus mu by sigma, and we will do the square of it. Is this part clear? How I
Sir,
write?
is there no inbuilt function for Gaussian mean rather than writing this formula?
For
That we
NumPy, it is not. Okay. There is this
Mhm.
random function for sampling from the normal, but there is not any inbuilt function in NumPy to sample to calculate the normal distribution.
In SciPy,
In SciPy, it is just like how I show you. Okay. From SciPy dot tab, SciPy dot tab import norm. Okay. This is
Sir,
there in
what is
SciPy.
0.5?
Okay, this is like the 1.1 by 2, right? In the exponential part, how it comes? Minus x minus mu square by 2 sigma square, right? So that 1 by 2, I have written it as negative 0.5. Okay. Like I can do in here 2 times sigma also. It's the same thing. But then it would be like I have to remove it from the square. And is it clear? This Gaussian function? Okay. So maybe I will write an equivalent part here also. What I did here. So it was the back 1 by sigma slash sqrt. Okay. Now I think one user will be this one. So will repeat every time. Okay, exp. Then we have this okay, so minus x minus mu. Okay. This whole maybe do by sigma. Okay. Hmm. Everything square. Okay. Mu by sigma. Okay. Hmm. Into now we want is the square of this whole thing. So okay, so okay, so it's not taking on the whole. Okay, maybe I will do it. Just give me 1 minute. So flat 1 by 2. P. Just give me 1 minute, okay? I will. Okay. For this expression, that is the density function. Okay, I written here. For this minus 1 by 2 that comes, I written that as negative 0.5. Okay. Rest is this, and this part here is this. Okay. Is it clear now? The Gaussian?
Sir, the format that you just typed, what is that called? Is it latex?
Yeah.
Or-
Okay. Let's take in Markdown. Okay. The Colab also use Markdown in the text. If you open any text file. Okay. Just like in our discourse, if you type in the double dollar, if you type an expression here, let's say x minus y. Okay, let's say x1 plus x2 equal to 5. Okay. So this got converted into a nice looking equation. Okay.
So, sir, is this does this work in Jupyter Notebook as well,
I guess
or
so.
only in Column? Okay, sir.
I'm not
Sir,
sure
can you
about
please copy paste this in chat window?
what.
It's 1 y sigma root 2 pi.
Okay, this.
E.
Okay, this double dollar means it will be like a container, means it will come in the center. And if you want to like do the inline, then you have to only use single dollar. The same way it works in our discourse also. Okay, discourse, the platform that we use for conversation. Okay, that also uses the markdown. Okay. If you want to practice the LaTeX, I would suggest you to go through the matcha. Do you know about matcha?
No, sir. Can you please ping? Can you in the chat window?
The document that I created for all the slides, I create them using matcha. Okay. If I show you, This was the today's document. Okay? So I created using Macho. Okay. So maybe you can learn this. Okay. I have given that Macho link in the what I say document also that I create.
Okay, sir. Thank you.
Okay, let's get back to the problem. What we have to do here is we have to sample. We have to find the density of the point 5 with mu 3. Welcome. With mu 3 and 1.5 sigma square. Okay. So just put Gaussian, and what we want is the density of 5 with mu 3 and sigma 1.5. Okay. So if we run the cell, okay. I forgot to run the above cell. Now let's run this. Okay. So 0.68. I guess we have made a mistake here. Now is the okay. Just there was one conflicting between the brackets. Okay. So I fixed that. Now it is more correct. Okay. So just pass the argument and we got this value. Is it clear for everyone? How you find the density? Okay. Or else you can also use this SciPy library. Okay. Just type this function and maybe you can then type what we say norm question mark. Okay. Okay. If you want to do it with SciPy, okay. First import this. And if, when you type this norm question mark, it will give you, it will open the document and you can refer how you can use this to do, okay? And this is the manual way. So,
Sir,
point
what
eight,
is the answer when we run this function? What is the answer?
this
0.109.
109.
Okay, sir.
If the answer is not matched, just put from
Yes,
bracket.
sir. It does not match. I actually I have got 0.6. It looks like I have
Same.
made some mistakes.
Yeah, I also did the same because I did not put this bracket, okay? So this
Bracket
bracket of
before
whole,
sigma. Okay.
yeah,
Okay, sir.
okay, for whole, because this whole thing is dividing, right? So just put that. Okay, maybe you will get the right answer now. Shall we move towards the next problem? Okay, good. The problem 8. Here we have to sample, okay, 1000 point from the Gaussian distribution with mean 3 and standard deviation 1.5. We have to calculate the MLE or estimator for the mean of this data set and 3. Okay, it's this. So as I showed you in the starting, this RNG has this function called normal. Okay. So let's say for what argument it takes. For this part, the question mark. Okay. What it does, it draw random sample from the normal distribution. Okay. And if you just scroll down to the parameter, first is local. Okay. That refers to the mean. The second parameter is the standard deviation. Okay. Third parameter that it takes is the size. Okay. And that's all we have to do. So the first parameter is mu. Mu is 3. The second parameter is standard deviation, that is 1.5. The third is the size, that is 1000. Okay. And let's name this as X. Okay. You will get your sample. And now what you have to do, you have to calculate the MLE. Okay. For the mean of the data set. What is the MLE for mu and normal distribution? What is the MLE for mu parameter in the normal distribution? Did you guys forgot? The MLE for the mu parameter is the sample mean again. right? So if you want to estimate the mean parameter, what you can do is just type x dot mean. Okay, and that is the MLE you will get. Okay. Any doubt, anyone till now? No. So let's move toward the problem 9. Okay. That is plot the histogram of the data set. Okay, that we calculated here. This. Okay, this. We have to use plt.hist. So again, if you don't know, just type plt.hist and it will open this document. Okay. So this text x. Okay. Now, if you see on all other parameter, this written none, none, none. Okay. Now, what does this mean? That they are not necessary or compulsory parameters. Okay. The only main parameter for plt.list method is x. Rest all other parameters are optional. If you want to give, you can give, or else it will take the default value, some default value. Okay. So let's first try with just x. Okay. And in the last line of this question, also tell. Okay, it's not. That's it. If you just type x. Okay. Now let me put one semicolon at time. So what this semicolon is doing, okay, by default Colab, what will it will do? It will try to print the output of the last line of the code. Okay. So if you don't want to do that, you can put semicolon at the end. Okay, then it will suppress that output. So when you will do just plt.hist, this is the histogram that you will get. Okay. Now it is not looking that good. Okay, so let's try and modifying some this. So what I will do, I will use this bins parameter and pass, let's say bins equal to 50. Now still this is not looking good. So if I make it 100, what about 200? Okay, now it's got worse. So let's get 200. Then you can answer how many. Let's try with some different value, 80. Okay, 50 is not good. Because we have information when it was granted.
Should we try with a low value like 10?
Okay, let's try with 10. 10, I guess it's default value. Okay, so what I was trying to find was some bell-shaped curve. Okay, maybe the data set is not sampled very good. Okay, let's leave it. Okay, or maybe I will just add the old.
Sir, we can use KDE to visualize the bill shape.
Okay, no, but I want it with the histogram, this method. Okay, let's leave it. But yeah, see, this bins basically controls the, you can see, okay, these bin sizes will increase. Okay, so, okay, let's leave it for here now. And let's move towards the last question.
Sir, can you repeat what you said about colon?
What I said about?
Colon.
Okay, colon. Okay. So see what Colab has do. Okay, let's say if you are doing some, let's say x equal to 5 and y equal to 3, and you just type x plus y. Okay, Colab will print the output of the last line. okay, of your code cell. Okay, it will automatically print. But if you don't want to do it, you can put semicolon at the end, and it will stop that. Okay, and if I remove the colon from here and then run the cell, you can see this this thing will come. Okay, that is just a general printing. It is basically printing this. Print to plt.hist. If you do, you will get this. Okay, but to suppress that, we will put semicolon. So we just only get the graph.
Okay, sir. Thank you.
The last question is about beta distribution, and we will stop with this. Okay, this is the last question for the session. We have given this different alpha, beta, gamma values. Okay, this is alpha and beta. Okay, we have to plot the beta distribution for these values. And it says do not worry about the normalizing constant. Okay, so if we'll use this plt.subplot, okay, and we will get we'll see how you can use this. So let's start. Okay, so I will first create one array param. Okay, this array will have the tuple of these parameters. Okay, so 5, 5, then 5, 1.5, then 1.5, 5, and then 0.5, 0.5. Okay, so just like before when we were doing with number of data points and that function value. Okay, we also created with one list there. Here also we are creating, but in the tuple list. Okay, it is a list of tuples. Okay, so alpha, beta, 5, 5, 1.5, like this. Next we will do is there's something called, okay, let's first see that. There's what we say, something called it linspace. Okay, what does this linspace do? If I type 0, 1, 10, okay, the output that you will get for this linspace is this. Okay, it will divide this 0, 1, okay, this line, and it will divide them in 10 equal points, okay, including 0 and 1. So the last, if you see, the starting is 0, the 1 is this, okay, then it got sampled 10 8 more points, okay, between 0 and 1 equally. Okay, so if I just do, let's say, put it to 2, it will just give me 0 and 1. Okay, if I put it to, let's say, 4, okay, let's not go with 4, let's go with 5. Okay, it will give me 5 equally distributed. Okay, 0, 0.25, 0.5, 0.75, and 1. Okay, so that's what linspace will do. Now what we will be using here is, suppose if you want to draw any curve. Okay, so the curve will look like, you want to draw the curve for y equal to x square. Let's say you want to draw this graph. The way to draw this graph is plt.plot. Okay, the x value and y is what? X square. So I will just, okay, and if you run this, okay, maybe not 0, 1, let's do it -2 and 2. So now it will basically divide points from -2 and 2. Okay, that's all. But if you see this graph, this is how it will look. Okay, so what NumPy is doing here to plot the graph, it is going to the basic. Okay, how in the school we used to draw the graph, we will take some points, okay, and connect them using straight line, right? That's what we used to do. Okay, NumPy is doing the same manner. As it has taken the 5 points, okay, so it is just joining them with a straight line. Okay, but you know that's not how the y equal to x squared curve will look like, right? It would be smooth curve. Okay, so what you have to do, you have to basically increase your point. Okay, increase the number of points that you will take. So let's try with 50. Now if you see, the curve is very smooth, right? Let's see it from full screen. The curve is very smooth now. Okay, and by default, if you don't give the argument this, okay, this third argument here, by default it will take the value 50. Okay. So is this linspace part clear? Why we are using linspace here? Okay, we will use this to plot, but we will be like, first of all, we will be plotting between 0 and 1 only. Okay, so x equal to np dot linspace. Okay, between 0 and 1. But now I will take the 100. Okay. I am taking 100 equally distributed point. Okay. So and I will put this about this. Comment sample, not sample, divide 0 and 1 into 10 equally point. 0, 0.1, like that. Okay. So now we have taken this line space. Next thing is we will use this parameters and plot the beta distribution graph. Okay. So anybody remembers the PDF for beta distribution? Anybody remembers the PDF for beta distribution?
PDF or beta distribution.
Yes.
Alpha by alpha plus beta, sir.
It is 1 by the beta function, that is the normalizing constant. Okay, I will show you. It is basically, if you remember from the Bayesian estimation we did, it is p power alpha minus 1 times p power beta minus 1, right? This one. Okay. This is basically the PDF, and we will don't include this what I say, normalizing constant. Okay, as in the question, if you read, it is given that do not worry about the normalizing constant. Okay, so this part, okay, this part here, this was the normalizing constant. Okay, so we will just focus on this part. It is p power alpha minus 1 into 1 minus p power beta minus 1. But here p is instead of p, we will use x that we use. Okay, clear everyone? So now we will just run for loop for alpha comma beta, because we are extracting the tuples in parent. Okay, in this list it will take this tuple. What would be our y? Y is this p power alpha minus 1 into 1 minus p power beta minus 1. So it is here x, so it would be x power alpha minus 1, okay, into x, okay, 1 minus x, 1 minus x power beta minus 1. Okay, I hope it is clear, and all you need to do now is plot. Okay, now there's something called as plt.subplot that it is given here. Okay, what you do when you want to like plot 3-4 figures or more than 3-4 fulfills fine, basically multiple figures, you are plotting multiple figures and you want them to plot in one frame only. Okay, there you use this plt.subplot. Okay, so here it is given one example, plt.subplot 2 comma 2 comma I. For this 2 comma 2 is kind of like your grid. Okay, so it will create four, you can plot here 4 figures, and it would be like in 2x2 manner, 2x2 matrix manner. Okay, 2 rows, 2 columns, and in each value it will be a one plot figure. What is the another way you can do? You can use 1 comma 4, in which 1 row 4 columns. So all your 4 figures would come in 1 row only. Another way is 4 comma 1. All your 4 figures will come in 1 column. Okay. This I refers to the index point. Okay. Means if 2 comma 2 comma 1 I will enter. So it will plot your figure in the first entry. If I will put 2 comma 2 comma 3, it will plot my figure in the third entry. Is this function clear? How it works? plt.subplot.
But sir, where we have defined this function, I do not see in this code.
This is the matplot. Okay, inbuilt function in
No,
matplot.
what I mean is in our Colab notebook, where is this function?
It is in C. This plt what? Okay, it refers to the matplotlib, right?
Right.
We go back here. This pl matplot.pyplot, this plt, okay, and it is the function defined inside this. Okay, so plt.subplot.
No, sir, that I understood. What I'm saying is, I think you have drawn the graph, right?
Yeah, I will do now.
So,
I will not draw.
oh,
I
okay,
will.
okay. I
I was
thought you
just
have already done. Okay, sir. But sir, why we have commented this green part here, np dot lineage space on this one?
This was I just used to explain you guys. Okay, so that's why I commented.
Okay, sir.
We are the linspace that we are using here is this. Okay, so now we will use this plt dot subplot. Okay, let's use the 2 comma 2 grid. Okay, I. As I told, I refers to the index. But unlike Python indexing, here indexing does not start with 0. Here it will start with 1. Okay, and also we have to found any way to access this iteration number also, like on which iteration it is. So what I will do is I will do this for I comma tuple alpha comma beta in enumerate. Okay, so what this enumerate, it will basically give the indexing. Okay, and that indexing is captured in I. Okay, and then this alpha beta will take the tuple values. Is this enumerate function clear? This enumerate, you can capture the indexing, and that will be stored in I. And as I said, unlike Python, in the plt.subplot, indexing will start from 1. So you have to do +1. Okay. So if I tell you how this loop will run, first it will go with in the starting, the I value would be 0 because here it is going with 0 indexing, enumerate. This alpha comma beta, it will take this 5 comma 5 value, and it will pass into this function alpha beta. You will get y value, and then you are using this plt.subplot, which will create a 2 comma 2 grid, and the indexing you will get here is 1 because 0 plus 1 is 1. So for this 5 comma 5, it will plot this graph in the first position, and then for the next it will in second, then third, and fourth. Okay, the next is just plt.plot x comma y comma, maybe I will give color sky blue. Okay, and I will create this also title so that we can refer to it, which uh, refers which one. Okay, so I will be using this what we say print formatting. Okay, alpha equal to alpha and beta equal to beta. Okay, so if I run this, you will get this graph. Okay, so for 5 comma 5, for 5 comma 1.5, for 1.5 comma 5, and for 0.5 comma 0.5. Is this clear to everyone how we created this? Any doubt anyone has in the code what any line will do? Yes, Cameron.
Sir, that enumerate part, sir.
Okay. So maybe let's use a different something. So L equal to 2, 3, 4. Okay. So what I will do for I and enumerate uh, okay L. If I will just print I, okay, this is what it gives. It is giving the indexing number 0 with that at the 0 index it is 2, at the 1 index it is 3, and at the 2 index it is 4. Okay. So in general, if you think, it is like in the same sense for I in the range type thing. Okay. So in that manner it will work, that when you do this I comma alpha comma beta, okay, what enumerate was giving us before. Okay, I deleted the cell. 5 comma 6 comma 7 for I comma I n. Okay. If you see the output, how it is giving, it is giving in the form of tuple, like 0 comma 5, where 0 denotes the indexing, 5 denotes the value at that index. So that's what enumerate function returns. If you go back, I have written it like I comma the tuple. So the enumerate function, when you will pass, when you will run on this param, it will give this 0 comma the first value, then 1 comma the second value in the list, and 2 comma the third value in the list. Okay. So basically it gives the index number and the value at that index in the list. Okay. In the form of tuple. That's what this returns. And because I written it in this way, for this I will store the index number only, and the value of that index is stored in this alpha comma beta tuple. Clear now? Okay, good. So
So
this
can we
is,
suppress this output,
yeah.
this IPython input this?
So just use this. Okay.
Actually, I tried,
It is
it's not happening.
Okay, maybe can we do it somehow? I hope it is.
If we do some plt.show, will it work?
Yeah. It will work in that way. It should work now. Okay, but okay. It is working. But it is creating in the last. So maybe will it work? plt.show. Okay, it will. Let's leave it here only.
So
It's better
now
in,
it has
yeah.
shifted from top to bottom.
Yeah. Okay, so maybe there might be any way. We have to look through the document, okay, for the matplotlib, if there is any way to suppress this output here. Okay, you have to look through the matplotlib document. I don't.
Sir, can you please share this collab notebook on chat window?
Okay, this one. Okay. Maybe I will upload this document. Will that be fine?
But sir, are you going to upload today?
Yeah, I will just upload after the session. So I
Okay,
hope
sir.
you know how
Then
to
it's fine,
find.
sir. Yeah, yes, sir. Then it's fine.
I'll just upload this. So just I will just tell you, okay. Those who don't know, in the master folder, okay, that's available in the supplementary content inside your portals, okay, you'll find this folder MLT T3 2024. In that, if you go in this live session slide, okay, there's this TA notes folder, okay. Inside that, there's this folder collab, okay. All the collab file that we will be discussing, either me, okay, or any other TA, whether Giri or Pranjal, okay. All the collabs that we will be discussing will be, you will find them here only. Okay, just click on collab, and all the collab that we have discussed till now, you will find them here. This is in total libraries. If you want to refer them, week 1, week 2, week 3, week 4, I will upload just now, okay, after the session. And all the notes, week wise notes, you will find them here. for week 1. Okay, for like week 4, that the session that I took the day before. Okay, that I have uploaded it here. Okay, so
Okay, sir.
you can.
Thank you.
Okay. Okay, so that's it for today, everyone. Thanks for joining and staying till the end, even though we went
Thank you,
one and a
sir.
half. Okay, welcome. Good night, everyone.
Thank you, sir.
Uh,
Nice,
Thank you.
sir.
Good
Bye.
night.
in the next session on Saturday, we will cover the programming assignment part 2 and solve with us. We will solve some question on estimation, GMM, and please, yeah, yes, Ravi.
Sir, can you share the link of the collab in chat?
Okay, this collab actually it is not getting saved yet now. I have to make the copy and download it and okay, so it will take. Don't worry, I will just share it. Just you have the portal link, right? Just open your portal, go to the supplementary content, go to the master folder, okay, in the live session slide, okay, there also you can. Or else you can go on the discourse. I have put the direct link for the TA session notes also, okay. From there you can access, okay.
So tomorrow's session is theory session, right?
Yeah, tomorrow is instructor session. That is also the theory session. And the next on the Saturday, we will be having the programming assignment 2 and solve with us session. We will solve some questions. Okay.
Okay, sir. Okay, thank you so much.
Okay. Welcome everyone. Thanks for joining. Good night again. I am stopping the stream now.
Thank you, sir.
Welcome.